The difference between an Euler path and an Euler circuit is the fact that circuits also have to cross every edge one time. Euler is every edge. To do a circuit, you have to start and end at the same point, and therefore all your vertices have to be even. Okay. Euler became quite famous for this. He actually proved those rules to be true. He didn't just guess and assume it was true. He's actually proved that those rules are true. So along came later a mathematician by the name of Hamilton. And Hamilton thought, well, hey, if you can pass through every edge once, I'm going to do the opposite. I want to pass through every vertex one time. So he tried to find a way to prove whether it was possible to cross through every vertex once. If you're doing a Hamilton path at the top, paths always start and end at different places. If you do a Hamilton circuit, he wanted to go through every vertex once, but he wanted them to start and end at the same place. But unfortunately, the downside of the story is Hamilton didn't get to be too famous with his theory because it turns out he never managed to prove it. There is no known method for knowing whether a Hamilton path or circuit is possible. We only can do it by just trial and error. Will it work? And so if you want to become mathematically famous, you need to develop a theory and prove it for how you know whether a Hamilton path or circuit is possible. So what I've done here is I've given you a graph down here labeled A, B, C, D, E. And I want to know, is an Euler path possible, an Euler circuit possible, a Hamilton path, and a Hamilton circuit? Okay. Eulers are easy. Remember, another E word. Eulers are easy. You check the vertices and you check their degree. So if I check the degree of these vertices, A is 2, B has 4, D has 4, C has 2, E has 2. You'll notice they're all even. So therefore, is an Euler path possible? Can I start and end, go through every edge once, start and end at a different point? Well, you'll check over here on the left. It says for a path to be possible, you have to have 2 odd vertices. We don't have 2, so no, an Euler path is not possible. If I ask you, is an Euler circuit possible? They're all even. So, yes, it's possible. And I'm going to ask you to name the routes. You have to go over every edge once. You can start anywhere you like. I'm going to start up at letter A. And from A, I'm going to pass down to D. So I'm going to go A, D. From D, let's go down to E. Get that out of the way. Back up to B. Okay, I don't really want to go back to A because I'll be stuck, so that can't be right. I'm up here at B, so the next best place to go would be down to C, over to D, or back up to D, I should say. We only have 2 edges left, so if I cross back to B, and then finally end up back at A, it works. Best thing to do when you're doing Euler circuits is to keep going in circles and completing circles as much as you can. Get back to where you started as often as possible. Okay. Hamilton paths, on the other hand, and Hamilton circuits are tricky. There is no known rule. You just have to be able to go through every vertex once. So that's a key factor. I have to go through every vertex one time. So I can start anywhere I like. Once again, I'm going to start with A. I'm going to highlight these vertices as I do them. I could go from A to D. I want to go through every one once, so I could go down to E, up to B, down to C. Did I do a Hamilton path or a Hamilton circuit? Well, I didn't end up where I started, so I must have done a Hamilton path. So yes, that one is possible, and it went A, D, E, B, C. Now, is a Hamilton circuit possible? Can I get back to where I started with one of these? So I would have to try again using a different color on my highlighter. Try blue here. Does anybody think I can get back to where I started? Well, some people will say, well, C's the hard one, let's try C. So they'll want to start at C, B, A, D. If I could go back to C, I'd be good. I could just go around that little diamond and I'd be done, but I can't get down to E. So obviously that didn't work. Is there a better place to start? Maybe I should start at one of the busy ones like B or D. So if I start at B, I could go B, E, D. But then where? I can either go up to A or down to C, but I'll never get to both of them without going through one that I've already crossed through. So since you can't do it without crossing through a vertex you've already hit, a Hamilton circuit is not possible. Okay, so there you go for Euler paths and circuits, Hamilton paths and circuits. That's part one. There's actually 4 parts here. The rest of the parts will go faster. Part 2 is what we call shortest paths. And shortest paths are you for trying to find a route to pass through here. I want to find the shortest route from A to Q. Now, this is what we call a weighted graph, because you'll notice each edge has a number represented in it. Those numbers could be miles, those could be cost, those could be anything in the real world that you want to connect. It could be the number of minutes from one place to another, lots of choices. But our goal is I want to get from A clear down to Q, and I want to find the shortest path. So should I go A down A, B, E, G? Should I go across the bottom route? Should I cut through the middle somewhere? Where's the best route? You'd go nuts trying to find all these routes yourself. There is a method for doing this, okay? And no one ever wants to do this method. I will tell you right now, number one, I'm going to rig on your project a problem that you won't get the right answer unless you do it my way. And B, you're going to have me really upset if you don't attempt to do this in the proper way. So when you try to find the shortest path, you have to test every possible route. But there's a system for doing it. We're going to start at A. One place I could go from A is C. So up here at C, I would write, I came from A, and so far I have traveled a distance of 2 units. I could also go to D, out here in the middle, so I would write there, I came from A, and I would have traveled 5 units. Down here at B, I could have also come from A with a length of 4 units. Okay. Now, you try to go somewhere else, and you need to check. From B, I could have gone to D. But from B, I'm already at 4. If I add 3 more as I go from B to D, that'll be 7. Will that be shorter than the 5 I already have? No. So I keep the 5. But where could I go from B? I could go down here to E. So I'm going to come from B. I had 4 already. If I add the 2 more from B to E, that's a total of 6 units I've now traveled. Keep working your way left to right. I bounce back and forth above and below. We could go to G here. So if I could come from E, I already had 6, plus 3 more would make me have a total of 9. Okay, so now it's decision time. F. I could come to F from point C up top or from G down below. You have to check and see which one is going to be shortest. I could also come from point D in the middle. If I came from A, 2 plus 5 would be 7. If I came from point D in the middle, where I already had 5, I'd also have a total of 7. And if I came from G down below, I already had 9, plus 1 more would be 10. So, which one is shortest? Well, since 2 of them are the same, pick whichever one you like. I like D. It's where I can easily erase, so I'm going to take the one that came from D, and I'm going to be at a total of 7. Now, I want you to note, if we choose that to be 7, are we at G down here on the bottom in the shortest route possible? And the answer is not anymore, because if F up here is a total of 7, as I come down to the bottom, 7 plus 1 as I travel this line would mean, nope, this baby isn't right. I should come from F, where 7 plus 1 makes only a total of 8. That's a smaller, shorter path. So you're always trying to get to the shortest path. Keep working your way to the right. The next point we haven't labeled is I. The question is, should I come from F or come from G? Well, if I come from F, 7 plus 5 makes 12. If I come from G, 8 plus 3 makes 11, so that's the shorter route, and I would say come from G totals 11. Next up is H. If I come over from F, 7 plus 2 is 9, which is going to be smaller than coming up from I, so I'm going to say I should come from F with a total of 9. Okay, now you can do J or K, it's kind of your choice. I'm going to go ahead and do J. Which one's shorter? Well, from H, 9 plus 4 is 13. From I, 11 plus 4 is 15. So, hey, I'll take the 13 and say I came from H. But we still will have one more to check in a second. I also need to do K. K has to come from G. 8 plus 6 is 14. So am I still the shortest route as far as 13? Yeah, I am. 13 is still the best way to get to J. If I came from K, 14 plus 2 would make 16, and that wouldn't be the smallest. I am going to go up to L now and come from J. 13 plus 5 makes a total of 18 when I get to L. Okay, getting to M. I could come from the top. At L, I would have 18 plus 1 would make 19. Or I could come from K. 14 plus 2 would be 16. That's shorter, so that's what I'm going to pick. K comes from 16. All right, let's do point N. Has to come from M. 16 plus 3 makes that 19. Coming from O, or going to O, I should say, from L, 18 plus 7 makes that baby 25. But check out P. You would think, why would I want to go to P? It's not on the way to Q. But watch, this is how this gets sneaky. If I came from N, 19 plus 1 is 20. So if I went up from P to O, 20 plus 2 would be shorter than the 25. So I should cross out this 25 and say, hey, dude, I should be coming from P with a 22. And last but not least, I need to go to Q. If I come from O, 22 plus 1 looks pretty good. That's only 23. However, I could come from N. I come from N. 19 plus 5 is 24. Which one's shorter? The one coming from O at 23. So it turns out the shortest route is going to be 23 units long. We have that answer. But then they're going to ask you to name that final route. Well, how on earth are you going to figure out what was actually the shortest route? Well, that's why we took these notes across the graph, because now you can backtrack your trail through the problem. If I start out here at Q, it says I came from O. At O, it says I came from P. And at P, it says I came from N. At N, it says I came from M. At M, it says I came from K, which came from G, which says I should go to F. F says I came from D, which then came from A. Now, if I had asked you before we started to pick the best route, would you have picked that one? No, I sincerely doubt it. I don't think you would have picked that one. So there's a prime example of why you use this method. And I will get rigid about the fact that you need to use that method, and I can set these up and make the numbers work so that I will get you unless you do it my way. So take advantage of that.